Okay, so here in this video, it's a follow-up to introducing the definite integral. Okay, so if we had the definite integral, say from 0 to 5 of a constant function 4 dx. So that would mean I would draw the constant 4. This is y equals 4. It's a constant line at 4 on the y-axis from 0 to 5. And I'd enclose that and get that as my area. Well, the base is 5 units long, the height is 4, and my area would be 20, which would mean the value of the definite integral would be 20 using area. Well, that was a nice one because of the fact it was a constant function and it ended up being a rectangle, a formula we know of. But we often know we get functions of this shape that are not exactly a semicircle, rectangle, or triangular region, or trapezoid. So how are we going to find the area or approximate the area under the curve from, say, A to B, from this x to this x? What we will do is we'll break up this region into equal partitions. So maybe we'll break it up into 4 equal rectangles. And we are thinking that, well, we don't really have rectangles yet. So what I will do is when I subdivide this into 4 equal rectangles, I end up with 4 equal size subintervals from this x to this x, from here to here, from here to here, and from here to here. So this would be my base in each rectangle, and that we will call is delta x. It's the change in the x's. And because we desire to break them up into equal widths, each of these will be the same. So the base of the rectangle will be delta x. Well, I need height now to get the area. The height will come from a y value. And what we will do is we will either choose in this interval the left endpoint, which would be here, or the right endpoint, which would be here, or perhaps the number in the middle called the midpoint. And to get that y value, we'll put that value into the function to get y, because you remember, y equals f of x. Okay, so let's get to the point.
Interruption, Sheila Briggs and Tamara Bordeaux to Mr. Pascal's now.
So suppose I have the definite integral from 0 to 4 of x squared plus 1 dx. And I want to approximate the value of the definite integral using area. Okay, so we are familiar with that when x is 0, y is 1. And when x is 4, 16 plus 1 is 17. So pretty high up there, and it's a portion of the parabola from 0 to 4. X squared plus 1 is a parabola, and this is a shape from 0 to 4. I'll enclose my area as such. And I'm going to choose to break it up into 4 equal rectangles. So what is the length of each base then? What's the size of each base of the rectangle? Well, delta x will be equal to b minus a over n. This is a, your lower limit. This is b, your upper limit. So it's going to be 4 minus 0. And n represents how many desirable rectangles you choose to have of equal width. So the 4 will go down there. 4 over 4 is 1. So that means each rectangle will have a base width of 1. So 0, 1, 2, 3, 4. Each of these is a width of 1. That's your delta x. Now, that's the base again of each rectangle. How will I get the height? Well, the height has to come from y, and the only way I can get y is by putting an x into the function. My choices are either I will choose the left endpoint of each subinterval, or the right endpoint of each subinterval, or the midpoint of each subinterval. So the x's in this are 0, 1, 2, 3, 4. And my subintervals go from 0 to 1, 1 to 2, 2 to 3, 3 to 4. Again, I'm breaking it up into 4 equal size subintervals where the length is 1, which corresponds to the base of my rectangle. Okay? The difference between each of these is 1. Now I'm going to choose the left endpoint of each subinterval to approximate this area. So the notation is left rectangular approximation method. Left rectangular approximation method. It's where I choose the left endpoint of each subinterval to get the y value. So the base here is 1, and I'm going to take the left endpoint of this subinterval, which is 0, put it into the function to get y, and I get 1. The delta x here is 1. I will choose between these two the left endpoint, which is 1, put it in, and get 2. Between these two, the width is 1. The height I'm going to choose is the left endpoint, which is 2, put it in, and get 5. Between these two, the base is 1, the difference is 1. I'll choose the left endpoint, which is 3, put it in, and get 10. Okay? So because the delta x was the same in each case, I really could have just pulled that out in front because it's a common factor in each of those areas. And what would be left would be f at 0, which is 1, f at 1, which is 2, f at 3, which is, this is f at 0, f at 1, f at 2, which is 5, and f at 3, which would be 10. So an approximation to this would be here 18 as an answer, using the left. Now, and where are the rectangles in this? Well, when x is 0, I follow it to the curve and I make a rectangle. When x is 1, follow it to the curve, make a rectangle. When x is 2, follow it to the curve and make a rectangle. And when x is 3, follow it to the curve and make a rectangle. So one would definitely say that 18 would be an underestimate of the actual answer because we're missing this area here. Now let's choose the right endpoints of each subinterval. So for the left, we got an answer of 18. Now in the right rectangular approximation method, we would again choose the right endpoints. So delta x is the same for each. We'll just pull out the 1. And between these two, we're going to choose the 1 now, put that in and get 2. Between these two, we'll pick 2, square it, add 1, get 5. Between these two, pick 3, put it in, get 10. And pick 4 now, because between these two, this is the point on the right. Put that in, 4 squared plus 1 is 17. And here we'll get for an answer 7, 17, and 17 is 34. Okay? Now when I draw the right rectangles, between here, I'll choose this is my right endpoint, follow it to the curve, and make a rectangle. Between here and here, this is the point that lies on the curve, so between these two, I make a rectangle. Now this is the right endpoint in this subinterval, make a rectangle. And between here and here, this is the right endpoint, make a rectangle. So one would definitely see that this would be an overestimate to the actual value. So for the right, I got an answer of 34. Well, I think we'd agree that a nice compromise would be the midpoint. The midpoint is found by adding the ends and multiplying by a half. So this middle would be a half. 1 plus 2 is 3, divided by 2 is 3 halves. 2 plus 3 is 5, divided by 2 is 5 halves, and 3 plus 4 divided by 2 is 7 halves. So these are the midpoints of each of those subintervals. Add the ends and multiply by half would give you those points. The width of each subinterval is still 1. So a midpoint rectangular approximation method would mean, because it's equal size, delta x is 1 in each case, so I have to put 1/2 in. So I get 1/2 squared is 1/4 plus 1, plus 3/2 squared plus 1 is 9/4 plus 1, plus 25/4 plus 1, plus 49/4 plus 1. And you can add them all up. You don't have to do each of them separately. 1, 2, 3, 4. And then I get here 10, 35, and that makes 84 over 4. And that gives us 21 plus 4 is 25. If we average the left and the right, we should get close to the midpoint. So if we add that, we will get 52 divided by 2 is 26. So you can see that the best approximation method is the midpoint, or taking the left and the right and averaging them. Now, how can we get the actual value? Well, there's a way we'll develop to get the actual value, but for right now, you can use the Math 9 feature on your 83, hit Math 9, and then you type in the function x squared plus 1, comma x, because it's with respect to x. The a value is 0, and the b value is 4, and that will give you the exact value. Okay, so let's just bottom line it now and do some problems. How do we make it short to the point? So suppose we have the definite integral from 0 to 3 of e to the x dx, and we want 6 equal subintervals. So first step is we need to find delta x. Delta x equals b minus a over n. 3 minus 0 over 6 is a half. Number 2, I need to know what the x's are in each subinterval. I start here at the a value, 0. Add a half to 0, get a half. Add a half and get 1. Add a half, get 3 halves. Add a half, get 2. Add a half, get 5 halves. Add a half and get 3. And you better finish right here. What are your subintervals? Well, they go from here to here, here to here, here to here, and then you should have a total of 6. 1, 2, 3, 4, 5, 6. Okay, of all equal width. They're all a width of a half. Third, suppose we want to do a left rectangular approximation. Then because delta x is the same for each, I can pull that out in front. So that's 1 half. That is the delta x. And in each of these subintervals, I will choose the left endpoint. So between these two, this is the left endpoint. Put it into the function to get the y value. So that's e to the 0 plus. Between these two, this is the left. I'll put it in, e to the 1 half. Plus, between these two, put the 1 in, e to the first. Plus, between these two, pick the 3 halves, e to the 3 halves. Plus, between these two, this is the left, put it in, get e squared. And then plus, between these two, this is the left, put it in, and get e to the 5 halves. And there's our answer. We can leave our answer sometimes in terms of e or ln's, or simply we can use our 83 to get an approximation. If we were to do the right rectangular approximation, then back in each of these subintervals, we would have chosen this is the right, and between these two, the right, and then between these two, this would be the right, and etc. all the way down. Just make sure you have 1, 2, 3, 4, 5, 6. Okay? Can't be one short or one more. All right, another different function. Let's do a trig function. Suppose we have the definite integral from 0 to pi of sine x dx, and n equals 4. So we're going to do delta x equals b minus a over n is the first step. It's going to be pi minus 0 over 4, or pi over 4. So in second step is to get the x's. We'll start here, add a quarter, add a quarter, add a quarter, add a quarter. My subintervals are from here to here, and I should have 4. 1, 2, 3, 4. Now let's do a right rectangular approximation method. Delta x is the same for each. I can pull that out in front. And now I will choose the right-hand endpoint in each subinterval. So between these two, this is the right endpoint. Put it in, and I'll get the sine of pi over 4. Between these two, this is the right, the sine of pi over 2. Between these two, the sine of 3 pi over 4. And between these two, the sine of pi. The sine of pi over 4, we should know, pi over 4 is a reference triangle, 1, 1, and root 2. It's y over r, that's 1 over root of 2. Sine of pi over 2 puts us up here, and the y value is 1. The sine of 3 pi over 4 puts you over here. Sine is still 1 over root of 2, it's positive in that quadrant, and the sine of pi is 0. So as an answer there, we would get pi over 4 times 2 plus 2 over root of 2, and of course you can work on simplifying that. Not 2, 1. 1 plus 2 over root of 2. Okay. Next is just one more function, is in terms of ln. So the definite integral from 1 to 4 of the ln of x dx. And suppose we want n to be equal to 3, and we're going to choose the midpoint approximation. So we need delta x, which is b minus a over n. 4 minus 1 over 3. 3 over 3 is 1. Number 2, to get the x's and to learn the actual subintervals, we'll start with 1 this time. We start here, add 1, get 2, add 1, add 1. And I should have 3 subintervals, 1, 2, 3. And now we'll do the midpoint rectangular approximation method. So between 1 and 2, the midpoint is 3 halves. Between these two, it's 5 halves. Add the ends, multiply by half. Add the ends and multiply by half to get 7 halves. The width of each subinterval is still 1. It's the same for each. So it's going to be the ln of 3 halves plus the ln of 5 halves plus the ln of 7 halves. And there's my answer, or my approximation, in terms of ln. Okay? And again, to get the accurate answer, we would go math 9 for right now. Hit the function ln of x, comma 1, comma 4. And that'll give us a more precise answer. Okay? The picture of, again, ln from 1 to 4. This is the graph of ln, and from 1 to 4, we'd expect that to be a positive answer, since the graph from 1 to 4 lies all above the x-axis. We're breaking it up into 3 equal subintervals. We chose the middle of each of these subintervals. So we take the middle, go to the curve. That's the y value we're getting off of. This is the ln of 3 halves. Make a rectangle. This is the midpoint. Go to the curve. Make a rectangle. This is the midpoint. Go to the curve and make a rectangle. Okay? So then a portion will lie outside and a portion will lie under the curve. And there's our approximation for that function from 1 to 4 of 3 equal subintervals. The question to consider is, how can we improve upon these approximations? So what we're coming up with are approximations to the definite integral by creating equal size rectangles, 4 of them, 5 of them, 6 of them, 10 of them. How can we improve upon our approximations using rectangles?